So, sort of a pre-warning. I've given this talk, and I feel like I've somewhat gotten it down a little bit, but the online version is something else because with something like this, you kind of like to draw pictures while you talk, and that becomes a little bit of a challenge. So we'll see how this goes. But I think going slower is better than going faster for this, and we'll get technical maybe with the second half of all this. So the focus of this talk is going to be on a conjecture by Milnor. It said the following. It says that if you have a complete manifold, if it has non-negative Ricci curvature, then the fundamental group should be finitely generated. And the focus of this talk is mainly to discuss a counterexample to the conjecture, and the examples and the theory kind of surrounding them are all joint with Ilya Bru and Daniele Simola. And so maybe where I'll start with all of this is to point out that actually the conjecture is remarkably close to being true. In particular, let me mention a result by Kapovich and Wilking real quick, which we'll circle back to later when we're doing kind of a formal literature background. So what the result says, which builds on a lot of work, is that any finitely generated subgroup you have is uniformly finitely generated. So what that means is that if by chance I had some finitely generated subgroup of the fundamental group and there were 1 billion generators, then in fact there's only 10 generators. Right? So you can't ever actually go beyond a certain number of generators. So as a consequence of this, you can't have things like an infinite number of z factors or an infinite number of z sub 2 factors or z sub p factors or so forth and so on. In fact, you can't even have more than some dimensional number of these things. So if you're going to have a counterexample to this, then it has to have the rather unusual property that every time you go up and up and up, and a new generator of your fundamental group suddenly becomes geometrically relevant. It actually had to generate the old generators as you're going through. There has to be something a little bit funky going on in that regard. And it's fun to sort of compare this to the context of second homology or second homotopy group. So in that case, one can build examples, and in fact, quite nice ones. So the first one's going back to Perlman, which were bounded diameter and non-collapsed, right? So probably this is an audience that appreciates that word that basically means really nice, right? That where the second homology was infinite, right? There was an infinite number of z factors appearing, and actually more recently, you can build some rather funky examples. If you go to the collapse world, you can even build limits anyway of things like this, where every open set has infinitely generated second homology. All right. So I mean, it can't be a manifold or it can't be anything nice. So second homology can be really, really wild inside these spaces. Maybe that's relatively recent work that's joint with my 2 students, Eric Hupp and Kai Wong, and Eric is applying for postdocs right now. So this is a good time to plug for him. So my basic plan here is I'm going to cover some background to the theory to kind of understand the various things that this conjecture inspired over the years, and what we can actually say about the fundamental group, and then we'll move on to drawing a bunch of pictures and trying to get some sort of idea of what the counterexample actually looks like.
Aaron, may I ask basic, maybe stupid question? So how about finally presented? Is it clear that such a conjecture is wrong, that the fundamental group is always finally presented, or is this irrelevant?
So I mean, I think the discussions we're having is that it does seem conceivable that it's finitely generated over the rationals, right? Something like that maybe is quite possible. In terms of finitely presented, so you mean the number of relations after the number of generators? That seems quite conceivable. Yeah. Well, generators is clearly infinite, but the number of relations actually might be controllable. This is actually a good question.
Okay.
Well, controllable mod the number of generators. You got to be a little careful how it's phrased, I suppose. Okay, so terminology as we're going through this. So MGP, pointed on Riemannian manifold. When I say M tilde, this means we're talking about the universal cover of the manifold. And really the only difference here in our discussions is that whenever I stick a tilde on something, that this means you should be viewing this as being equipped with some sort of action, right? So this is really a space with an action, and that's how you should be thinking when you see it. The Riemann curvature operator. So usually I give a basic spiel around here, around this point of the talk. I think for this audience it's probably unnecessary. So the curvature operator, right? It's the anti-symmetric part of the Hessian. This thing is not zero unlike Euclidean space, but it doesn't depend on derivatives of z, which is kind of surprising. The correct way to kind of morally understand this, though, is as the Hessian of the Riemannian metric. And my clicker is no longer working. Aha, there we go. So that is, if I have a Riemannian manifold with bounded curvature, you should be kind of viewing this the same way you would a function with C2 bounds. It should have much the same behavior. And in particular, that this is sort of why analysis is so well behaved on spaces with bounded curvature. And it also gives a nice interpretation of Ricci curvature, because Ricci curvature being the trace of the curvature operator, if we're interpreting the curvature operator as the Hessian of the metric, right? So it's like a 4 tensor and the metric is a 2 tensor, so it kind of behaves the right way. Then its trace should be like the Laplacian of the metric. And this gives more or less a 20-word explanation as to why Ricci curvature appears everywhere when we're doing this. It's the same reason that whenever you do analysis, Laplacians appear. They just kind of have a way of appearing. So I think what I'll do, since I've only got 40 minutes, is actually skip my usual Betty number bit, but I'll say what the answer is and then skip the rest of the talk. But what I typically do at this stage is the following. I try to give some sort of background as to why one might actually expect Ricci curvature to actually control fundamental group in the first place. And to do that, I sort of go through in one slide what my introduction to geometric analysis class looks like, which is that we want to go through the Hodge theorem. Right. So there's a very clear connection between Ricci curvature and Betty number from the point of view of the Weissenbrock formula, which lets you control the Betty number of your manifold. So in particular, if you have non-negative Ricci curvature, your Betty number has to be bounded by n by basically an integration by parts trick in the end. And this is hardly the full fundamental group. But what it is it's the rank of the torsion-free part of the abelianization of the fundamental group. So it's some tiny little piece of the fundamental group, which is at least enough to give some sort of base intuition as to why one has some hope that Ricci curvature controls fundamental group. Actually controlling full fundamental group requires a full structure theory. Like that, there's no introduction to geometric analysis argument to do that. But it is nonetheless a sort of insightful way to see that there should be some connection between the two. Okay, so that being said, what I'm going to do now is I'm going to jump ahead to the background. So let's discuss a little bit the history of the conjecture and some of the major progress toward it, just so we can get a sense of what's known and maybe by the end of Daniele's talk have some sense of how the counterexample actually sort of waves its way through all these various theoretical results popping around. So the first result out there is to John Milnor in 68. And what he proved was the following. He proved that if Ricci curvature was non-negative, then finitely generated subgroups of the fundamental group have polynomial growth. Right? So this sort of very abstract condition on group generation. It's fun to sort of mention that the proof is based on Bishop volume comparison, so that this actually sort of predates the Gromov Bishop volume comparison, which is a word we hear like every 3 days. And this is obviously what led him to the original conjecture in the first place. So what he can control, right, is basically the growth rates of these finitely generated subgroups, which is maybe where the intuition for why you should be finitely generated in the first place is. So what is certainly true is that they have polynomial growth, and the growth is at most the dimension of the manifold. So there might be some hope in there that you've actually got full control over your space. It's also sort of fun to point out that he didn't call it Ricci curvature. He called it mean curvature. So at this point in the literature, it hadn't really quite been decided whether to call it Ricci or mean curvature. There seems to be literature on both of these things. One can understand why Ricci eventually won out. Mean curvature tends to have too many meanings. So the next result in this direction was by Gromov, who prove that the polynomial groups are almost nilpotent, right? And so, this was an extremely abstract theorem. It had nothing to do with Ricci curvature, right? This is simply about the behavior of groups with this polynomial growth condition. But as a nice consequence of this, when you combine it with Milnor, right, what you get is that manifolds with non-negative Ricci curvature have almost nilpotent fundamental group. Now, what's not controlled by this is the notion of almost. Right. So we don't know really the size of the finite part at this point in time anyway. But we do have that most of it's got to be nilpotent. It's fun to point out that this is where this notion of Gromov-Hausdorff convergence really first came to play. I'm sorry. Okay. And if you know anything about the proof of this, this should be really quite surprising. I mean, these two notions are not one that if you don't have your head into everything, you would expect to necessarily be connected. So it's worth pointing out that results by Wilking and in particular Way were provided a semi-converse of this. So what they proved was that all finitely generated, almost nilpotent groups can arise as a fundamental group of a space with non-negative Ricci curvature. And the real break in that was by Way, which, if I'm not mistaken, might have been her graduate thesis. It's a 4-page paper, which is just lovely. And what she did was provide the first example of a space with non-negative Ricci curvature that had a nilpotent lattice as fundamental group. And there's a subtlety here that's really worth pointing out, because there is a conjecture by Fukai and Yamaguchi that basically says this can't happen under non-negative sectional curvature. If you have non-negative sectional curvature, the fundamental group should be almost abelian, right? So what Way really showed with this example was that this conjecture has to be false in the non-negative Ricci case, and, as phrased anyway. Now that conjecture, by the way, is still open. And Wilking took this example and basically built on it in order to see that actually, well, anything you want can really appear. Anything that's a finite extension of that anyway can appear as a fundamental group of a space with non-negative Ricci curvature. Wonderful. Okay. So next, so the first real positive result in the direction of all this was by Gromov, who was actually, if I remember my literature correctly, was studying bounded sectional curvature at the time, but sort of buried inside this thing. He proved that if you have non-negative sectional curvature, then the fundamental group has to have at most a finite number of generators. So in particular, the Milnor conjecture holds for non-negative sectional curvature. The proof itself is based on the Topological triangle comparison theorem, which is a highly sectional curvature thing. And essentially what that allows you to do is take what's happening at infinity and pull it into something that's happening at some sort of finite amount of space. And once you kind of understand that, finite generation becomes at least intuitive, right? If what happens not too much can happen locally, kind of just certainly intuitively. So if you can take what's happening at large scales into what's happening at small scales, well, you're going to control everything in the end. And there was an extension of this result that is somehow more technical in nature, but it's really worth pointing out, I think, even at least as much for the proof as it is for the result itself. So Fukai and Yamaguchi, what they did is they proved a local version of this. So under a lower sectional bound, they proved the so-called local fundamental group, which maybe for our discussions isn't so important, but what it is take the fundamental group of loops in a ball, but look at those loops that are contractible in a bigger ball. That way you have some wiggle room, right? So the image of your fundamental group of a ball in the whole space, if you want, right? And they showed that was uniformly finitely generated and almost nilpotent. And their proof was completely different. It relied on a complete, to be able to make this local statement, that they needed a full structure theory of lower sectional curvature in order to pull this off. And what's going to be kind of important down the road is that their ideas will generalize to Ricci curvature in a few minutes. Actually, and also, if I'm being really fair here, what they proved here is uniformly almost solvable. That this is an extremely subtle point, and it was extended by Kapovich, Petruin, and Tushman that uniformly almost nilpotent. And this finally gets us to the state of art. So in 2011, Kapovich and Wilking extended Fukai and Yamaguchi's proof. And proved the same thing for Ricci curvature. So if you have a lower Ricci curvature bound, then the local fundamental group is uniformly finitely generated and almost nilpotent. And how that relates to say, even the Milnor conjecture is simply that's if we apply this to a space with non-negative Ricci curvature, where local is basically anything you want now because of the scales, then if you have non-negative Ricci curvature, finitely generated subgroups are uniformly finitely generated and uniformly almost nilpotent. Right. So as soon as it's finitely generated, it's got a finite number of generators, period. Right. So you can control dimensionally the number of generators that can actually occur in this case. So that this was if you have a billion, you have 10 argument from the beginning. And this is what rules out things like too much torsion, things like too many Z factors. So if you're going to have a counterexample, it can't be like that in the end. By the way, you guys can interrupt me if this is too fast or too slow.
Aaron, excuse me, would it make any difference if we looked at manifolds of positive Ricci curvature? I mean,
no. Our example has positive, or at least you can whack it to make it have positive. Yeah.
Okay.
Mm-hmm. I don't think we're that careful about it, but it definitely can be. That's a fair question. Probably we should say it that way. And my last little points on some sort of background results here is going to be the following. So it turns out the conjecture's been resolved in low dimensions. The main thing to really emphasize here is that every time the Milnor conjecture has been resolved, it's really because people have proved vastly stronger results, and the Milnor conjecture is an obvious consequence of it. Beginning in dimension 2, it was proved all the way back in 35 that if you have a two-dimensional non-compact space with non-negative Ricci curvature, then you're either flat or diffeomorphic to R2. Either of these will sort of trivially imply the Milnor conjecture because you really understand what you're staring at now. This was extended some 50 years later by Shane and Yao to dimension 3. So that is under the assumption of positive Ricci curvature, strictly positive now. They were able to prove that a three-dimensional non-compact manifold has to be diffeomorphic to R3. A fun point here is that this paper sort of is a bit distinct from every other piece of literature I'll talk about here in techniques. Namely, it uses minimal surfaces to prove this. There are actually quite a few papers out now. It's almost become a bit of a theme to assume non-negative or positive Ricci curvature and say things about minimal surfaces. But this was actually the case where you use minimal surfaces to say something about spaces with Ricci curvature in this case. And finally, it was extended by Liu, again, some 30 years after that, to the non-negative case. So he handled the case where you have non-negative Ricci, at which point you're either diffeomorphic to R3 or you'll isometrically split or at least recover well as R cross a surface, at which point, again, Milnor obvious consequences of all this. I mean, this is much, much stronger. And let me also sort of mention the following. Milnor has been resolved under a variety of geometric constraints. So the other sort of really popular thing to do here, but it would involve me taking 5 or 10 minutes to make so many definitions that I think I'd rather just sort of say it in words real quick, is that, controlling the fundamental group is very much connected to what can happen at infinity in these spaces. These are non-compact spaces, and so you look at them at larger and larger scales and sort of see how they behave. And under various constraints on the behavior at infinity, people can prove Milnor, right? So the people that are deserve mentioning here are Lee, Sormani, Wei, Pan, have all proved nice results along this line. Usually along the lines of say tangent cone uniqueness of the universal cover or splittings of factors and things along this line. If you can control basically the behavior at infinity at all, you can typically prove Milnor in the end. And these guys are the ones who put this all together. I probably won't get there. Maybe Daniele will. But the behavior at infinity of this space is kind of fun. Like you can see how it just swings through all these various results. All right. So to the point. So basically, based on all the sort of results being written down here, the fundamental group of a space with non-negative Ricci curvature is actually pretty well understood. Certainly, finitely generated subgroups of it are very well understood. They're uniformly finitely generated. So the counterexample is going to look like the following. So the theorem is the following. So let gamma be any subgroup of Q mod Z. You should be thinking of Q mod Z here as the rationals inside the circle. Then there exists a smooth, complete 7-dimensional manifold with non-negative Ricci curvature, which has this as a fundamental group in the end. So some points kind of worth mentioning. So first, there's two primary examples that we'll kind of stick ourselves to in our discussions. One is Q mod Z itself. So that is all the rationals inside the circle. And the other is the dyadic group. So that is all the rationals that have some power of 2 on the bottom. The primary reason for this is that Q mod Z actually has the most fun geometric behavior. So when I talk about the geometry, so different choices of gamma will give different geometries and they'll behave in different ways. But the one for the full rationals is the most fun. So usually when I talk about the behavior of this thing geometrically, I'm talking about that guy. However, for whatever sketching I do today of the example, there's a lot less notation for the dyadic group. And that just sort of spares us a little bit of pain as we go through. So I'll probably restrict to the dyadic group when we actually discuss pictures involved. But I'll try to point out how these things differ in the general case. It's the same moral, but more notation to keep in mind. Also, key point, note the following. Every finitely generated subgroup of Q mod Z is actually generated by a single guy. So Q mod Z, the rationals in the circle, clearly infinitely generated group. But if I take a subgroup and if it's finitely generated at all, it actually has to basically be generated by its shortest element. So it'll end up being just a finite group that's generated by one guy, no matter what, right? So this is, if you're trying to find a counterexample, this is sort of what it has to be. You have to look for something that has this sort of behavior. So when you keep going up to infinity and you get your new generators, they've actually got to generate the old generators as you go down. And it's worth maybe pointing out the following. So if you've never thought about this before, then even building any manifold at all with Q mod Z as a fundamental group is a little wonky. So there are some known topological methods for doing this. Probably the most geometrically popular one that people would talk about is the Dirac solenoid complement that lets you sort of build such a space. So our topological construction is actually distinct, right? So this is as it turns out, a new way of building spaces with fundamental groups that are infinitely generated in this sense. I gave a talk in front of a very painful talk in front of a bunch of topologists precisely to kind of confirm whether that was true or not. For us, of course, we built it geometrically and then after the fact asked what's the thing look like and tried to understand it. Okay. This is a really good time for questions because the talk gets more painful at this point. Very good. Okay, so then let me start with what time I have to kind of outline some of the steps of these constructions and draw some pictures for you. And then we'll take a break and Daniele will pick it up again. The way I'll do this is I'm going to sort of give a vague and broad overview of the whole thing, and I'll use a bunch of words and draw some pictures. And then as with whatever time we have, I'll kind of keep going through it and adding a few more details each time and using a few more words in the hope that as we keep circling around it over and over again, it'll be kind of crystallized in our heads a little bit. So let me first sort of point out that the construction never focuses on M itself. It's always going to focus on the universal cover together with building an action. So we want to build some large space together with a free and proper discrete action by gamma. And for our conversations, I'm going to focus on the dyadic group 2 to the minus j, generated by all the 2 to the minus j's. As I said, this will save on some notation. It has the rather disadvantage that it sometimes when you make too many restrictions, it can sort of hide some important points behind what's happening. But I'll do my best to point that out as we're going through anyway, and see if we can survive through that. So the construction is the following. So some of these pictures will kind of appear and disappear several times. So it's inductive in nature. So that is for each j, I'm going to want to build some mj or mj tilde if you want, but which will be some complete manifold with non-negative Ricci curvature, and it's going to have a free and proper action by capital gamma sub j, which will be a finite group. So capital gamma sub j should be a sequence of a nested sequence of groups. Let's draw a picture real quick if I can. Gamma naught, gamma 1, gamma 2, gamma j. So with actions by these gamma j's, in this particular case, capital gamma sub j is going to be generated by 2 to the minus j. So it'll be basically add one more. Each time we move from mj to mj plus 1, I'm going to have a slightly bigger group action on this guy. So we'll have basically one extra action on the space when we're actually done. And although it may not matter too much yet, let me point out, just so that when I point it out for the third time, it starts to be clear, what this sort of sequence of groups looks like if I'm viewing this as living in the circle. And this is where I really want a pointer, but oh well, I guess I'll just use a different color or something, right? So our first guy is a single point generated by gamma naught. Our second gamma 1 is generated by so we have twice as many generators, gamma 1, and when we square gamma 1, we get gamma naught squared. Our next generator, we double the number of elements again in our group to get gamma sub 2, so we're 1/4 of the way over. We square that, we get our generator gamma sub 1. We square that, we get back to gamma sub 0, and so forth and so on. So every time I go from mj to mj plus 1, I sort of double the number of elements inside the circle that I actually have. So the construction itself is going to involve 3 main steps. So I will primarily focus on discussing and visualizing one of these steps. So the place to start is the following. So topologically, right, what we're going to be doing here is taking a lot of copies of S3 cross R4 and gluing them together in some fairly wonky ways. So our base sort of background space that you kind of always want to start with, we're trying to build MJ in the end, like this J step of our construction. Where we'll start with simply an S3 cross an R4, as the picture shows, but it's going to be equipped with an action by this gamma sub J. And what's important, and we'll say what that action is explicitly at some point, but the main thing to keep in mind right now is that the action is quite crazy. So the action is going to rotate the circle factor, the S3 factor, in some fairly reasonable way, but it's going to be rotating the R4 at the same time. But as J gets big, it's going to be rotating the R4 faster and faster and faster, right? So we've got a pretty wild looking action that's kind of doing that inside of our space, right? But the space itself is quite simple. It's S3 cross R4. I'm drawing R4 with a little bit of a bin just to show some positive curvature, but this is where we kind of start. And what we're going to want to do in order to build MJ from MJ minus 1, what we're going to basically want to do is take 2 copies of our MJ minus 1, which we've kind of already built, and they're going to also kind of look like R3 cross R4 at infinity in some sense. And we're going to want to glue 2 copies of that into our new copy of our S3 cross R4 in order to extend our action. So the picture is this. And I'm just going to have to draw on top of that because I think if I'm not pointing to things, it's impossible. So that is, we start with our S3 cross R4, and then we want to glue in 2 copies of the space we've already built into it. And now the goal is, remember that gamma sub J versus gamma sub J minus 1, our new action that we're trying to extend to, right? It basically has this one extra action to it, right? When you square it, you get the old action that was from our last space. So what we want to do with that new action is just map this copy of M sub J to that copy. And then when we square it, it'll come back and map our original copy of M sub J minus 1 back to itself, but not by the identity, by the old action, right? So we're just flipping it, we're just sort of doubling it so that we can add this extra, Z sub 2 kind of looking action, right? Where we square it back, but it's not quite a Z sub 2 action. It's got to go to the old action in the end. So the idea being is that, if we can do that, then we can do that over and over and over again. And then what you kind of build from this is this sequence of spaces with these larger and larger group actions as you're moving along. So the picture at this point should be, simple enough if you don't think too hard about what's happening. So in some sense, what's the problem with this picture? Why doesn't it work quite so easily in the end? And the reason it doesn't quite work so easily in the end is that, so as I said here, this gamma sub j action here on this S3 cross R4 is quite wild. It's rotating the S3 and it's rotating the R4 very, very, very fast. I mean, how on earth do you glue that action in with if this mj minus 1 looked kind of the same, but with gamma sub j minus 1 as an S3 cross R4 infinity? So it had a wild action. I've got two wild actions. How I'm going to glue this in so those actions commute is not only unclear, it's simply not possible the way it's being written. So this falls apart because the action's just too wild. I need to calm the action down in order to be able to have some hope of making this gluing construction actually work in the end. And that enters us into step 2, which is really where all the meat is in here. Oops. Oh. There we go. Good Lord, I hate this thing. You know what? I'm just going to erase those. Success. Okay. Okay. So step 2 of the construction is the following. We're going to start. So at the bottom of that picture there, what you've got is our picture from last time. We've got this S3 cross R4. Fine. It's got this. You can ignore the m sub j minus 1s there. We haven't really done the gluing yet. All you have is an S3 cross R4, very simple, but with a crazy looking action. And we're going to have some in-between region here where actually what it looks like is a cone over S3 cross S3, sort of a fun point, right? So if I remove a neighborhood of the cone point of the cone over S3 cross S3, that's topologically the same thing as taking S3 cross R4 and removing a ball in R4, right? So these things sort of match up correctly. They all have boundaries which are S3 cross S3. So in the middle will look kind of like a cone over S3 cross S3. Some craziness is going to go on that I'm going to kind of describe in a few minutes. And when you come back out of it, you're going to look like a very simple S3 cross R4 again, just like before, except our action now is going to be really simple. So when we start at the bottom, we have this crazy action down here that's rotating both factors. And after we do some unwinding through the middle, what we come out at the end is an action by the same space on S3 cross R4 once again, but you're only rotating the S3 factor. You're not rotating the R4 factor. So we've unwound this action to a very simple action at infinity. And this is something which I more or less claim you can sort of re-glue back in the past discussion and then sort of iterate on this construction as you keep going up. Okay. So now let me sort of mention the subtle headache that's floating in the background here. So these actions here are gonna, so we'll write them explicitly, but they're not complicated. So S3 right has a natural S1 hop action on it where you can rotate. R4 has a natural hop action on it where you rotate the S3 sphere inside of it, right? So these actions here are all going to be actions that rotate both factors by the hop action at some speed or another. So down at the bottom here, we're rotating the first S3, not so bad. We're rotating the R4 very, very fast. When we get to the top, we're only rotating the S3 action. And if you think about this for a few minutes, these two actions on what are really S3 cross S3 aren't homotopic actions, right? So somehow I've started with an action on this boundary, which is where all the gluing takes place. S3 cross S3 are the boundaries. And I've got an action at the bottom and I've got an action at the top on S3 cross S3, but they're not homotopic actions. How did you actually start at one at the bottom and into the other one at the top? And the reason is that what's going to have to happen to make this work is that we're not really unwinding the action. What we're doing is winding the space. So the S3 cross S3 at the bottom and the S3 cross S3 at the top aren't the same S3 cross S3s. They've all meshed together by the time you get from the bottom to the top, so that when you get to the top, it looks like an action that only rotated that first circle, that first sphere. But that first sphere is not the same as the first sphere at the bottom. Right? So we're continuously connecting non-continuous things by actually changing the domain, not the action itself, as we move up. This is somehow going to be the trick. Okay, and then once you can unwind the action, I think all this is just what I've been sort of saying. The third step is just to do the gluing, right? And then this may be, there's some work to be done to actually make it preserve Ricci curvature in the process, but maybe one can believe that if you unwind the actions enough, you can figure it out. Okay. Excellent. And there's the full picture once again, drawn a little bit nicer. So again, just to use words, we'll have S3 cross R4, we'll have a wild action, we'll move up, it'll be an unwild action, then we'll want to wrap it around and glue it into another copy of S3 cross R4 and do it again. And each time we do that, we've doubled the number of actions we have on the space until we get something infinitely generated. So we do it infinitely often. And we don't have to worry about all that technical nonsense for that. Okay. So maybe before starting over, what I'm going to do real quick is I'm going to give you a topological perspective of what this gluing actually looks like and what actually happened.
Sorry, can I ask someone something? Yeah. So if for some reason these two actions were homotopic, then would this mean that your construction gets much easier, or then?
Actually, that's not even clear to me. It's not even clear to me that it would get that much easier. You still got to move from one to the other somehow.
Right.
But as it turns out, they're not homotopic for like theoretical reasons.
Good. Okay.
Yeah, that's fair. Okay, so what I'm going to do real quick is I'm going to try to discuss basically what I just discussed, but from a purely topological perspective. I'm going to ignore all the geometry I've already floating around. This has the advantage of giving you some picture of what the space actually looks like globally when we're done with all this. And also it gives you a topological understanding of when I'm talking about twisting, what am I actually doing in the end, or at least what's the non-geometric consequence of this, the topological consequence of this twisting that was going on. So again, reminder that by the way, and I'll point it out because it'll occur again down here. In the picture, I was gluing 2 copies of this m sub j minus 1. That was because every single time, this was the dyadic group. So if we were doing Q mod Z instead of 2 copies, you might have some finite number of copies that actually get glued in that have to do with how these this various nested sequence of subgroups relate to one another. But so instead of 2, it's something else, but same deal. So let's talk about the topological construction real quick. So we can build the universal cover with a tree of sorts. So what I want to do is I want to take an infinite number of copies of S3 cross R4. So that's kind of like the picture we were just having here, and associate to each copy that I wanted a vertex for my tree. So each of these vertices in the end is supposed to represent, over here, for instance, is supposed to represent 1 copy of S3 cross R4. And there's going to be an infinite number of these things in the end. And then each directed edge here is supposed to represent that this copy of S3 cross R4 is supposed to get glued in to that copy of S3 cross R4. And the gluing will take place the way the last picture sort of showed, right? We'll remove a ball from this guy and then glue in this guy into it through the S3 cross S3 boundaries. The reason that each vertex here has 2 directed edges going into it is, again, because we're the dyadic. So like in the last case, every time we had this S3 cross R4, we had two of the last guys being glued into it. There's always two gluings in each S3 cross R4. For Q mod Z, it might be more. So the number of vertices for each, the number of edges connected to each vertex may change if you're doing Q mod Z here in general. So, I mean, what you see here for one point actually is that so you've got this almost sort of fractal structure for your space at infinity, because this keeps going on forever and ever and ever. So there's sort of a geometrically fractal behavior of how this thing is actually working. And the second thing really pointing out is that the gluing maps here, the map that took our copy over here to our copy over here, this twisting that was geometrically occurring, the effect of that is that these gluing maps are not by the identity. We're not mapping S3 cross S3 into S3 cross S3. In fact, we're not even mapping them in a way that's mapping class trivial. So they're not even homotopic to the identity, as it turns out. That's what this non-homotopy thing actually really kind of comes down to. So each of these gluing maps we have here are actually going to be represent a non-trivial element of the mapping class group, and we'll glue them all together and designed specifically to preserve this action from one step to the next. So the action globally makes sense as we're moving around. And what that sort of lets us do, and okay, so we start at 4 minutes late. I'm going to take my 4 minutes if that's okay, just so I can get through one statement before I.
No, sure. Yeah, take your time. Yeah.
So if these gluing maps are mapping class non-trivial, then and our goal here isn't just to build a space with Q mod Z as a fundamental group. Our goal is to build a geometric one for which we actually have a geometry on this thing. Then this begs the question that we need to understand something about Ricci curvature in the mapping class group, at least Ricci curvature in the mapping class group of S3 cross S3, which is where the gluings are really taking place. And so to that end, I'm going to state a lemma real quick. And it's worth pointing out that this lemma isn't actually, this is more of a corollary of what we use. What we use is a slightly more complicated version of this, but I think it's actually easier to get our heads around this lemma first. So I'll state this guy, and then there's a equivariant version of this actually floating around that we prove. So lemma is the following. So take S3 cross S3 and let G naught be the standard metric on it. So two copies of S of your sphere. Let G1 basically also be the standard metric, but let it be written as being pulled back by some diffeomorphism on S3 cross S3. So, geometrically, we're used to just calling those the same thing. Like we don't even worry about that. But I'm saying, let's worry about that for a minute. So we have G naught, which is the standard metric. We have G1, which is the standard metric, but written in terms of these new coordinates on S3 cross S3. Then the claim is that there's a smooth family of metrics, G sub t, with strictly positive Ricci curvature, bigger than 6 maybe, which connects the two. So as a reality check real quick, if this diffeomorphism is homotopic to the identity, then this is a completely ridiculous statement. Because what I could do is take my G sub t to all be just pullbacks of the standard metric by some diffeomorphism and then go from G naught to G1. If, on the other hand, this phi represents a non-trivial element of the mapping class group, that is, it's not homotopic to the identity, then these metrics G sub t in between are going to be really, really wild. They're going to be all over the place. But regardless, you can't actually connect one to the other. The reason to want to kind of think this way is we're used to sort of modding out by diffeomorphism groups when we think geometrically. But topologically speaking, it is much more appropriate to mod out by the identity components in the end. Because when you do these gluings by things that aren't in the identity component, you don't preserve topology. So what this is saying is that, if we look at the space of all metrics, mod the identity component to the diffeomorphism group, then the mapping class groups acts on the space of metrics. And in particular, the standard metric is some big, large, discrete subset in there, but it's in the path kinetic component of in the space of positive Ricci curvature of the standard metric in this case. Okay, and I am out of time, so I'll just quit and let Daniele deal with the rest. Thank you.